Hi guys, I just want to say something before I start with the video. I want to give credits to some of the people who found this stuff. And please join the Fortnite Explorers server. We share stuff that we found there, link in the description. After that, we can start.
Scene. We've been investing in our animation authoring tools with Control Rig and Sequencer, and we've now reached a very important milestone. For the Fortnite was rigged and animated entirely in engine with no external DCC used. And so far, we've produced over 240 minutes of animation for LEGO Fortnite across gameplay, emotes, cinematics, and trailers. Their system generates a vast amount of unique tiles, which are then assembled on the fly to compose a unique world for each player to experience. Our learnings translate into new ways for you to use a framework, develop new tools, and create your own gameplay opportunities. To get you started, we are also releasing a PCG biome creation plugin as a concrete example of a flexible, data-driven tool with built with a systemic approach featuring the latest improvement.
Another component we've added is LiveLink. This is another huge thing that has really modified our pipelines. So LiveLink is a plugin. It brings in a node onto your animation blueprint, and that node essentially works like an animation sequence player or a slot. And you could have the LiveLink node anywhere on your anim blueprint, and that LiveLink will listen to Maya or Motion Builder and some other apps and stream in that data real time. And so in this case, we have Maya on the right of the screen, and of course we have Pi on the left. And our biggest use case in the beginning was actually marketing shots. Lighting in Maya does not match lighting in UE4. And an animator would spend a couple hours trying to get a very nice facial pose for a marketing shot. But the minute you bring it to the Unreal Engine with different lighting, that facial pose would not look great. So this allows the animator to instantly see what the lighting situation looks like when they're modifying the face. Another component of Fortnite is that we each have a host of different skins that all share animations. And if we are doing a marketing shot, we want to make sure that shot will look good on the actual skin. Well, in Maya, everything is animated on the character you see, Jonesy. He's like our basic default medium male. All animations, all emotes are animated on him or the female version. And so this allows us to still modify that animation pose in Maya and see it on whatever skin we're going to ship with. And it allows us to, get around clipping issues. In cases where the character has a lot of anim dynamics and cloth, it allows us to see how our animations will react with those in real time. This sped up iteration big time because used to, you do an animation, export it, import it, see the results, and restart the process again. We also use LiveLink for motion capture. So Fortnite is all hand-keyed animation. The pipeline for Fortnite that's just where the line was drawn. It's hand key only. However, Paragon was motion captured mostly. So what we would do is go to the mocap studio, load up LiveLink plugin so we could actually see our avatar as they would look in game, and it would allow the actors to see what they look like. I mean, it gave them a virtual mirror where they could actually walk up to a big screen we had on the mocap stage, see themselves as the character they're playing. So LiveLink has been huge for us. And like I said earlier, here's an example of we could test out emotes on different characters that might have skirts, dresses, capes, and other things. We could see how our animations react with those in real time. And the next thing I want to cover is a pose asset. So whenever you're rigging faces, each face has its own assortment of poses. So I don't know if any of you guys have used face effects in the past or any other facial systems. They generally require like a fax-like pose list that can be like 20 to 50 to 200 poses. And we have a new asset now in Unreal Engine 4 called the pose asset, where you can store these poses. And each character will have their own pose asset, but they can share animation from other characters. So let me give you an example. So each of these characters have their own pose asset, so they each have their own custom sculpted poses for their needed list of fact shapes, but the exact same animation is driving them. And the animation that is driving them is float curves. So each pose node has like an associate curve, just a float curve. So it's not baked joint data. It can be, the float curve can drive poses. The poses can be created with joint offsets or blend shapes or a combination of both. And so in the case of Fortnite, this allows the animator to create one animation performance, say for an emote, but it will carry through to different characters. And we also wanted to see how far we could push this concept. So one of our riggers took...
Work with this feature on your own. So what is Control Rig? It is based on our Blueprint visual scripting system. It's basically used to control properties in order to drive animation. It uses a much lighter weight virtual machine to translate your code than Blueprint. It's mostly to copy and execute your code. As you can see from this screenshot, it is a graph-based node interface that uses special rig units that manipulate bone transforms. Control Rig is primarily used for procedural animation as well as complex retargeting solutions. We do have a retargeting solution in place now, but that's only if your skeletal hierarchies are very, very similar. If you have more custom needs, Control Rig can help with that. We're going to show that a little bit later, as well as animating with Control Rig sequences. So that's my one slide overview on Control Rig. There's no better way to show it than to jump into the editor. So I'm going to go ahead and do that. And let's go ahead and jump over to the editor, and I'll just undock this. So this character on the left here is one of our characters from Fortnite. We're going to be doing some stuff with her today. On the right, we have our Unreal Engine. And the first thing that we're going to need to do is enable the plugin, which we can do by going to Edit and Plugins. And over here under the animation section, we have a Control Rig option. Now it's disabled by default. You'll need to enable it and then restart the editor. Just to save us some time, I've already enabled it and restarted the editor for us. Once you do that, you're going to get access to two new assets inside of the content browser under the animation section, one being the Control Rig Blueprint and the other being the Control Rig Sequence. Now we're going to be working with both of these here during this session. But first, we're going to work with a Control Rig Blueprint. And we have a scenario that some of you may encounter when you're animating characters or working on your own project. So our character on the left, our Fortnite character, we have this animation of our character. And she's kind of throwing something, which looks pretty good. She's throwing a grenade or a frisbee or a paper or something. And this looks great. We like it. However, our design team, our artists, they come to us and they say, you know what? We want to add some more flair to this character. We want to allow them to be able to customize this character. Maybe they have a big shoulder piece, or maybe this character has something like this gauntlet piece here. And now you can see we have a problem with our animation. The claw is actually clipping into the fingers here. Now we have a dilemma. We could go back and animate the claw piece separately and have a whole slew of animations to match our character animations, but that's a whole lot of work that we don't want to do. So Control Rig can help by procedurally animating this claw based on the pose from our actual character. And that's what we're going to set up here today. So to do this, what we're going to do is we're going to right click and we're going to create a Control Rig Blueprint. And when we do, it's going to ask us to pick a parent rig class. 99% of the time, you're going to be able to use the default Control Rig class. However, if you have some custom things that you need to do, you can create one in C++. It'll be available for you here. But we're going to use the default one, and I'm just going to click Create. And I'm going to call this the rig_gauntlet, like so. And I'll drag and drop it, move it into my gauntlet folder just to keep it nice and tidy. Perfect. So now what we can do is double click and open this up. And now we have the Control Rig editor. So if any of you have worked with animation in UE4, this may look very similar to an animation blueprint. There's a little bit of things that are different, but kind of recapping really quickly what we have a viewport where we'll see our skeletal mesh that we're going to be working with. We have our graph where we're going to set up our scripted scenarios. We have the details panel for properties, etc. Compiler results, I'm going to close that because we don't need it. But the main difference between this and an animation blueprint is this section down here. We have a rig panel, which is going to show all of our nodes that we have in our graph here and allow us to quickly jump between them. Directly next to that, we have our hierarchy. This is the joint hierarchy that we're going to be manipulating through Control Rig. And we can add one by right-clicking and going to Import and selecting the mesh that we want to work with and its associated skeleton. So I'm going to choose the gauntlet here because that's what we're going to be working with. And you can see it populates it with all the bones in that gauntlet piece that we can start manipulating. Now we want to see it in our viewport too, so I'm going to come over here to Preview Scene, and just add our mesh like so. It's super tiny. So I'm going to undock it, put it over here, and focus in on it. Perfect. So on the right, it's our piece that we're working with. On the left is our control rig. All right, so the first thing that we need to do is get a reference to this hierarchy so that we know where all the joint transforms are. We can start manipulating them with control rig. First thing we're going to do is right click and we're going to look for a rig reference or rig ref. And that is this node here if we select it. So this node contains all of this information. It knows where all these joints are at any given time. I'm going to give this a better name than the default name here. I'm just going to call this base hierarchy. Like so. It's our base hierarchy. Perfect. Now, for testing purposes, we want to be able to manipulate the finger inside of control rig here and then procedurally animate the claw piece based on the position of the finger. So the first thing we need to do is give us the ability to manipulate the finger. And we can do that by adding an apply FK or forward kinematic node. And you can see we can specify the joint that we want to manipulate. We can specify the transform that we want. There's some additional options here as well, but the first thing that we need to do is plug in our reference to our hierarchy. It's color coded, so the nodes will match up. So we got to take our hierarchy reference and just plug that in like so. Next thing we need to do is specify the joint that we're going to be manipulating. In this case, it's going to be this top piece up here. So it's going to be the whole finger we're moving with this node here. So I'm going to copy this by right-clicking it, like so. And we'll paste that in. Perfect. All right, so now we need to supply the transform in which we want to move this joint. Now we're going to need two things. We're going to need to know where we started and where we currently are in order to do that. So we can right-click and we can say get joint transform. And we can plug in the joint that we're looking for, which is that joint there. We're going to need to know the current position. And we're also going to need to plug in our hierarchy reference so we know which joint we're talking about. I'm going to copy this and paste it. And we're also going to need to know the initial the local position of this, so the bind pose. We can plug that in like so. Now you can see it spits out two transforms here, and we can manipulate those transforms by using a control node. The control node takes in a base, or our current. It also takes in an initial transform. So we can plug that in like so. Now you can see it spits out one transform. Now we could plug this directly in, but we're going to get some issues here because we need to be able to manipulate the finger relative to its current position. So what we need here is a get relative transform, taking in the result from wherever we move it based on the current. So let's plug that in. Now we get that final output and we can plug that in like so. And the last thing I'll do is just rename this so it's a little bit more descriptive. We'll call this the finger control, like so. So now if we compile and we go back to our control node and I come over here, I can move the finger up and down in the viewport like so. And as we do this, the claw piece is what we're going to set up next to move based on the finger's position. Now there's one other thing that we're going to do. We do this as a bit of a housekeeping, kind of let you test things out inside the editor. If I select this node here over in the details panel, all the way down at the bottom, there's a property called execution type. Where is this node being executed? Is it always being executed? Or if I click this drop down, is it only being executed in editing time? So inside of control rig only, because we want the animation to drive the finger. We don't want this apply FK to actually manipulate the finger. Only in editing time we want that. So it's purely for testing purposes. So I'm going to change that over and we should be good to go. So now we can set up the claw piece to move based on the finger's position. And essentially what we want is this top piece of the claw to move based on where we move that finger. So to do that, what we can do is copy this apply FK, change the joint that we're manipulating, which is going to be this one here. And in this case, we're making it additive. We're adding to it. We'll take our hierarchy reference and plug that in. And all we're really worried about is the rotation. We don't care about the translation of the claw or the scale. All we're really wanting to do is rotate it. So what we'll need is a couple of things. Similar to before, we'll need to know where we started and where we are currently. So we'll copy both of those, paste those down here. And for this, these are both going to need to be local. So we'll set it current local and initial local. Plugging in our hierarchy. So, and we'll expand the pins here so that we get just the rotation. Now we're gonna need to do a little bit of vector math to get this to work. I'll try to get through it as quickly as possible. Essentially what we need to do is for the initial local here, we need to get the inverse of this and multiply it by its current position to give us the delta. So we could say multiply by its current to give us the delta. Once we have that, we can use a get angle around a given axis. And what this allows us to do is if we expand the axis here, we can get the angle around the X, Y, and Z axis. And if we look at our claw, down in the lower left here, it might be a little bit hard to see, we have our X, Y, and Z coordinates. Z is up in blue. So we actually just want the Z axis so we can swing it up and down. That's all we're really worried about. So we can zero out the X, and we can make the Z 1, because Z is 1 is up, like so. Now that we have the angle, from that axis and angle, we can get our rotation and plug that in like so. So with all of that, if we compile and we go to our finger control, now when we move the finger, the claw automatically moves along with it. Now the finger's kind of clipping into the claw just a little bit. To kind of fine tune it, we can add an offset to this. But a quick shortcut that I'll do is to take the joint below the one that we're actually manipulating and use that as my initial local. And that'll pop the claw up off the fingers a little bit better. So now when we manipulate it, it looks a little bit better. So this is one part. We're moving the top part of the hinge. We can take it a step further and have the digit of the finger actually manipulate the top part of the claw here. Fortunately for us, the script is going to be pretty much the same. We just need to change which joints we're manipulating. So I could copy all of this data here, just daisy chain it off the end, plugging in our hierarchy reference again. So, and we have one more we need to plug in there. And defining the joints that we're manipulating. So it's actually going to be this joint that we're manipulating now instead of that joint. So I'm going to copy this joint, paste this in. So, and to give us that offset again, I'm going to take the joint below, just like we did before. So we'll do joint 2 as the offset. And instead of claw 1, we're now manipulating claw 2. So this part of the claw versus that part. So if we compile, before we do that, just housekeeping, I'll make this the digit control. Perfect. So if we compile now and we select the digit control, now we can move the actual individual finger to get that part to move. This is all great. Now, there are some edge cases with this. For you animators out there, you're probably like, what about this? When I go like this, we're gonna have some problems. So if I were doing this for real, I'd probably take into consideration what the other fingers are doing. But for the sake of this demo, I think this will be just fine for now, for the animations that we have. I think this will work. The last thing I need to do is make sure that on this digit control that we are setting this to only occur in editing time, because the animation is gonna drive this. So our setup is done. What can we actually do with this now? If we go back to the editor and we go down to the content browser, we can create an animation blueprint out of this gauntlet by right-clicking and going to animation blueprint. We can double-click and open it up. This is the final pose that our skeletal mesh will enter. What we can do is use a copy pose from mesh node. And what this does is over in the details panel here, if I enable this checkbox, use attached parent, it's going to get the source from whatever we attach this to. So the pose data is going to come from whatever we're attached to. In this case, our character. So I'm going to click this checkbox to enable that. Last thing that we need to do is add a control rig node, which is new to animation blueprints. And you can see it just takes in a source pose and spits one out. So if you've worked with animation blueprints, you can do things like blends, you can do layered blends, you can do additives, all working with control rig as well. But for our demo, all we're going to do is plug in the output from our copy pose from mesh, plug in the output to the final, and making sure that we assign our rig gauntlet, like so. And when we compile, it should be good. Now, the last thing that we need to do so that we can test this inside of the editor, we're going to go back to our skeletal mesh. And over in the details panel, all the way down here under skeletal mesh section, we're going to assign a post-process anim blueprint so that it can run in the editor here. And when I assign this, check out what happens to the claw here. It updates based on the position of the finger. Now, there are some artifacts from the glove texture appearing, which I'd probably want to mask out or not even include, but we have a much better result than what we had before. So now as the character is throwing that claw piece, opens up based on the position of the finger. versus what we had before. And this is all being done procedurally, so I don't need to go in and hand animate any of this stuff. A lot better situation. If we take a look at another example here, here's an example of our character doing kind of an emote. You can see as she points, the claw is open. It's a little bit better versus what we had before. So one more time, here's our end result. Perfect. So she gives me the thumbs up. Sweet, so that's one example of using Control Rig for procedural animations. You could do this for like we did the claw, shoulder pieces, attachments, all that can be driven dynamically with Control Rig. Let's take a look at another example if I hop back to my PowerPoint here. So we did procedural animation, retargeting solutions. We are currently using Control Rig for one of our characters in Fortnite. We have this werewolf character here on the left here, and to give you some context, all of our characters in Fortnite, all of their animations were created with a normal humanoid biped in mind. So hips, knee, ankle, foot. Kind of like this baseball pitcher in the back. So we have the hips, the knee, the ankle, and the foot. However, with our werewolf, we have this additional joint between the knee and the foot. So we can't directly take all of our animations and pass those over to our werewolf character because the joint hierarchy is different. So that's where Control Rig comes in to help. We're using that to solve that for us and retarget those animations. To give you some context onto how Fortnite characters are created, we have this concept of a base skeleton. It's just an invisible skeleton that everyone shares. There's no skeletal meshes attached to it. And that base skeleton is what drives all of our animations. Because that base skeleton is shared across all the characters and it's the same, all characters can share animations, except for our werewolf character that's a little bit different. The character skins are layered on top of that. These are the individual skeletal mesh pieces. So the backpack, the body, the head. If any of you have played Fortnite, all the custom different pieces that can go on, get layered on top of the base skeleton. So how do we transfer the animation from our base skeleton over to the werewolf? So here you can see the green is the base skeleton playing this jog animation, and the werewolf with the gold skeleton, the upper body, the joints are the same. The lower body, the joints are different. So the lower body doesn't know what to do with that animation data. Now, we tried to do some things like IK to solve this problem, just a pure IK solution, but that gave us an effect that was undesired, kind of the dreaded puppet pulling effect as the IK targets, or the IK is trying to reach their intended target. So it's not ideal. And if we take a look at this example, a more pronounced run, kind of like a crouch run, it looks not how we want it, so it's kind of undesired. So how can we use Control Rig to do this? Similar to what we did with our gauntlet, at a high level on the bind pose, we figure out the delta transform between the bones in the human leg and the wolf leg. We then apply transformation on the incoming human leg to generate the animation. So at an even higher level, we're just basically defining the rule set in which to apply the rotation. That's what's going on in the blueprint here, and that's what we did in our gauntlet. So we're doing this for various joints along the skeleton to achieve the desired result. We then incorporate it into an animation blueprint, similar to what we did before. And we do still use IK to fix up some of the feet, but most of the retargeting is handled by Control Rig. It gives us a much better result. The best part about this is that all of this was done in Control Rig. There was no need for a programmer to help. I am not a programmer, so I would not have been able to do this without the help of Control Rig. You can see the full blueprint graph here from a super high level. That's all there is to it. And on the left, the more pronounced run animation with Control Rig and IK. Looks a lot better. So that's another example is for retargeting. I'm going to give you one more example. As I promised, it's going to be kind of a sneak peek at what's coming. One of our tech official documentation pages, you can search our doc pages for Control Rig. It'll come right up. That's all the time I have. Thank you guys so much for sticking around. If you guys enjoyed it, thank you so much. If I have any questions, feel
into the anatomy of a Fortnite character, and that will give you a reference frame for other features in this presentation. So a character skin is actually composed of multiple skeletal meshes, and the first one being the base skeleton. And we also call this the invisible one, and that's because it's actually a skeletal mesh that doesn't have any skin geometry, so it's basically just a bare skeleton. And on top of that, base skeletons, and that's to make sure we can accommodate the different sizes of character, but also differentiate between the different genders as well. Something to note about this is that the hierarchy, so the topology of the bones of these skeletons are all exactly the same. And we actually lock the rotations in Maya, and that's because that helps us when we do our runtime retargeting. But that means that any translations in the bone can actually, that's what gives it the different shape and proportion of character. So now we have a mesh, now we have a skeleton, so now we need to animate it. So our basic character animation is driven by a single animation blueprint that's run on this base skeleton. And when I'm talking about basic character animation, it's locomotion, using weapons, or playing emotes. And in our case, most of the animations are actually authored on the medium-sized base skeleton. And then at runtime, we actually retarget it whenever this animation blueprint is used on a different skeleton as to which the animation was authored on. So this gives us an overall pose for the character, as I said, the main character animation. And then the individual character parts use that animation from the base skeleton, and we can actually copy that because the character parts share a subset of the base skeleton's hierarchy, so we can directly copy over that pose data. And each of these individual character parts will then have their own animation blueprint that drives the animation data for those leaf joints and adds the procedural animation. And as you can see in the image, this is an animation graph where we take the copy pose from the base mesh, and then in the middle we run some anim dynamics to add the procedural animation, and that's the final pose for this character part. So that's just an overview of how we build our characters. And that brings me to what it looks like. This is what the character part looks like. What we did, we added the 3 bones to the character part itself and kept the original human bones as well, so we can transfer the animation at runtime. And that means that the geometry of the part is actually skinned to the dog legs rather than the dog bones rather than the character bones. So this is what it actually looks like if you just use the copy pose. You can see you have a basic, the character's motion is basically working except for the legs, and that's because the legs are of course skinned to the dog leg rather than the character leg. So the first thing we tried was to use IK to drive the animation of the dog bones, but as you can see that falls apart really quickly, and in even more extreme pose it almost looks like it's a puppet that we're pulling on with strings. So what we need to fix this is basically some custom retargeting, right? Because we want to go from the human leg to the dog leg, and then we can always use IK to make that pose better. So the feature we used was control rig, and just a quick refresher on what control rig is. Control rig is our in-engine rigging system, and it's actually graph-based, and the nodes in this graph are called rig units, and they have the ability to modify transforms for a specific pose. And whenever you create one of these control rigs, it actually shows up. You can actually use it in the animation blueprints, and it just shows up as a regular node, and it will take an input, a pose as an input, and then we'll run the rig units to modify this pose according to your predefined behavior, and then output the pose when it's finished. So this specific solution, we take the relative transformation between the bones in the character leg and the dog leg in the bind pose, and then we use that to transform the animation data to make sure we can transfer the animation from the character leg to the dog leg. And this is what it looks like visually. So what we're doing here is we're taking the information for bone 1 and 2 and moving it over to the dog leg. Because the third bone doesn't actually exist, we don't actually have the ability to transfer any animation, so we'll need to solve that in a different way. And then the foot bone is still the same, so we can transfer that as well. And as you can see, the pose looks much better now in comparison to just using IK. But if you look at, for example, the feet, you can see the dog leg bones actually don't reach the targets that were actually defined in the character animation. So what we do is we add IK to make sure we hit those targets, and this is how we actually, this is what the final pose looks like in the game. And this is the extreme pose as well. And the really cool part is that this solution was completely created by our technical animators. That means there wasn't any need for an engineer to create this native node or go back and forth to define this behavior, where normally you'd be working with a technical animator creating a native solution, and then it might not be totally what he's looking for, so you need to go back and forth. But this actually shows how powerful it is to just completely be able to do this in the engine. And on the right, you can actually see because we didn't actually have any support for animated bone translations, you can see in this specific example, whenever the character lands, you can see the spine compresses on the medium mill, but whenever the retargeting is done to the large mill, this is completely lost. And that's because of the different scales of the skeleton. So we actually do our retargeting in 2 steps. The first step makes sure that we transfer the animation from the source skeleton to the target skeleton. And that happens, that's set up in the animation blueprint. As you can see, there's a couple of animation sequence players here, and each of them has a property called the retarget source, which basically maps to the skeleton this animation was authored on. And whenever that skeleton is different than the base skeleton this animation blueprint is running for, we need to do some retargeting. But this also allows us for a lot of flexibility, because you can use animations that were authored on all types of these base skeletons and run them in the same graph, which makes it very... Earlier we locked rotations between all of these base skeletons, so we actually don't need to do any retargeting there. And the scale gets picked up whenever because of the proportions between the different skeletons. So that means translation is the last thing that remains. And we used to have 3 modes to actually do this retargeting. The first one is skeleton, and that means it takes the translation from the skeleton in bind pose. So for this specific example, what we're trying to do is we're trying to pull the clavicle node up, but because the bind pose is static, nothing actually happens. The second mode is animation, and this will take the translation from the animation data, but that means that between all of those different skeletons, the bones will always be in the same place, because we're just using the translation and we're not doing anything special with it. And that means we had this extra mode called animation scaled, and this means we're still using the translation data from the animation, but we're now scaling the length of the vector according to the ratio between the base skeleton and the retarget skeleton, and that makes it so it's offset correctly. But this still left something to do, because now we have the correct length, but not the correct orientation. So we simply added something called orient and scale, and this reorients the translation and scales it as well by using a delta between the bind pose of the source and target skeleton, and this was already available in 420. And this is what we mainly use on the most of our bones on our characters, and whenever we have a bone that doesn't need retargeting, we use the animation mode, for example, in this case, on the root. So this is what the same example looks like. If you look at on the right, you can now see whenever he lands, we actually get that squash effect working as well, which was something that we were looking for. But whenever you start retargeting animations from a smaller to a larger character, you might start to miss these contact points. And in this example, there's a clapping emote where on the medium male the hands actually reach, but because the larger male character has much broader shoulders. And in this specific example, normally the hands are independent of each other, so we don't have any information for it, and it's just driven by animation. So what we did is to actually solve this problem, we added a bone that describes the relationship between the two hands. That means that we now have a bone that describes where the hand should be. And in the example GIF, you can see on the animation transfer one, you can see the bone in orange is actually showing where the hand should be, and the white hands don't actually reach those targets yet. But when we use the space switching IK, we can now make sure we drive the hands using IK and make sure that they still clap, so to say. And those curves are just stored on the animation sequence, and then they're used inside of our animation blueprints to either drive animation nodes or rig units to do this specific IK. So just a quick recap, this is our entire retargeting process. We start with the source animation data. If we only use the copy pose, you can see that it's a very scrunched looking character. His shoulders are looking weird, his wrists are doing something funny. So that's where the orient and scale comes in. Now we have the correct pose, but we start to see we're missing these contact points, so finally the space switching IK gets us there. And we actually use space switching for other things in Fortnite as well. In this example, there's parent-child bone fighting in this animation, and that's because the guitar was childed to the arm bone or the hand bone, and because we have this large swinging motions, whenever we're interpolating between those keys, there might be some precision issues which cause this jittering effect. And as I mentioned, because we use this more extensively, we want to be able to have something to fix this up in the engine. So back in 4.14, we added virtual bones. And virtual bones allow you to define a new relationship between bones, just as we did with the clap. But you can do this in the engine, so you don't need to re-import any animation data or go back to Maya to fix this up. So for this specific case, what we did is we reparent the guitar to be in chest space, and because the chest is more static and won't have this large swinging motion, it's much more still. And then to fix up the hands, we transfer the hands to be in guitar space, so we actually get the correct motion. And this is actually what it looks like in the anim blueprints. And this again just shows how powerful animation blueprints are, and blueprints in general, because content creators are very flexible into what behavior they're running animation blueprints. So as of 4.20, you are now able to run animation nodes natively driven by float, bool, or curve values. And that means it removes the overhead from converting or fetching data in blueprints. And this is an example of it. And as you can also see, it reduces the amount of clutter in your graph as well, because normally you would need 3 nodes to do this. So you get the curve value, and then you would negate it to get a correct alpha range, and then you feed it into your IK node. But that means that the first 2 nodes are actually executed in Blueprint VM, which makes it slow. And then on the right is the exact same behavior, but just as a single node. And as you can see, we define the name of the curve, and you can actually do any transformations on the value of that curve as well. And to actually make this a little bit more flexible, we added different methods of processing or transforming the value that is read. So before we had biasing and scale and clamping, and in 4.20 we also added range remapping and interpolation, so you can all do this natively rather than needing to do this in a blueprint. And for bool value specifically, you're also able to define the blend in and out times, the blend function you want to use, or even define a complete custom blend curve to do this blending in and out of a node. So that's some stuff we added to the animation blueprints to make them faster at runtime. So now combining these two, we now have the ability to animate a crowd. And as you might notice, all of them are using the same pose. So we needed the ability to add some variation. And you can actually add variations in 2 ways. The first one is you can set up different animation assets per state, which means you could have different idle animations or running animations. Or you can you have the ability to set the number of permutations per animation asset, which means we offset the start time of the animation into the clip. So if you'd have 2 permutations, the first clip would would start at 0%, the second one at 50%, and then that makes sure that we don't actually have these matching poses. So this is what it looks like when we add a little bit of variation. It becomes much harder to find the identical poses. So next up is on-demand states, because what happens when we need to play a timed animation? For example, when we hit a character or we kill a character, it needs to play an animation at that specific time. We can't just jump into a looping death animation because that might look very weird. So on-demand, basically, whenever a character enters this state, we kick off an instance that plays this animation. Whenever it's finished, it either returns to its previous state or it moves to a new state. Last. So for example, if 4 frames ago an AI started dying, we just reuse that instance rather than spinning up a new one. So combining that all, we now have looping states, we now have on-demand states, so we can do attacks and hits. But as you can see, any transitioning between the 2 states looks rather gnarly, and that's because we're just popping between them. There's no blending. So for blending, what we actually do, we take the poses from the 2 states that the instance is moving between, and then we use an animation blueprint to blend those 2 poses, and then we distribute those over the instances, which is really cool because whenever 2 or 3 or an X number of AIs are actually moving between the same states, we can actually share this blend as well. And just at the same as with the on-demand states, you have the ability to limit the number of blends happening concurrently. Again, for scalability, using it for scalability. So this is what it looks like with blending. We now have the looping state, the attack, and now we blend between them. And you can see it's a little bit more smooth than just rather popping. So the last thing we added was additive animation. And this was to, for example, whenever a character is running towards you and you hit it, you kind of wanted not to stop running, but you also wanted to give some feedback to the player that's actually hit. So for additive animations, we take the state that the character is currently in, and then we apply the additive animation on top, so you actually get a response as well. And this entire system is completely data-driven. So we have a single repository defining the states, the variations, the blend in and out, the blend in times for the specific states whenever we're blending. And also we have some per platform scalability settings, which I'll get back to in a minute. And this is actually what it looks like, what the debug view looks like. The top row actually shows the blend instances. So you see them kick in whenever a character is moving between instances, and the bottom row is actually the individual states that are running to drive these poses. And I hope the video works. Yes, there it is. So you can see the characters running around, and then you can see the different states kicking in, and whenever they're moving between states, you can see the blend. And when you start hitting him, you can also see that the death animations are starting to be used as well. It's rather fun. And that's that. So go and check it out. It's a plugin. It's very customizable for your project because most of it is data-driven. But we're always welcome to hear your feedback and see how you're using it. And as a little bit of detail on how it performs, this is an actual crowd of 200 AIs, and it actually takes a little more than 1 millisecond to do all of the animation, generating all of the animation poses. And you can actually add another 200 AI and keep the same number of poses, which means that you wouldn't actually increase your CPU usage to actually animate this entire crowd. So that's animation. And for animation, we use these values to drive something called update rate optimization, and shorthand URO. And what this basically does, it limits the amount of ticks. It changes the rate at which an animation or skeletal mesh is ticked. So on the left, you can see it's ticking every frame. The next image shows it ticking every 4 frames, and even next one's even 10. And then another thing you can do with it is actually disable interpolation, and that's because whenever you do interpolation in between ticked frames, you're still going to pay a game thread cost for that. So if you want to decrease the usage even further, you can opt to do no interpolation. But the thing, so the first thing we needed to add, or the first thing we found, was that you need a minimal bar for quality, and this is again very similar to dynamic resolution for rendering. How it's actually implemented. First of all, it's released in 4.22, so you can start using it. And that brings me to the skeletal mesh amplifier. And in 4.22, we now have the ability to do skeletal mesh reduction as well. We already had static mesh reduction and proxy load as well, but we now also have the capability to reduce your skeletal meshes. And it's actually 6 times faster than our previous solution, while still using an edge collapse algorithm. And on a per lot basis, you can set the target for the number of triangles or the number of vertices you want to end up with. And in addition, you can also reduce the number of influences per vertex according to the number of bones you want to be able to influence them. And again, when you're working on new features, you find problems. So in our case, because the character parts are all separate and they'll be reduced in isolation, we started to have these cracks at where the meshes originally met. So to address that, we have the ability to lock free edges. That means that any free edge on your mesh will not actually be reduced whatsoever. And this makes sure that we preserve continuity between the individual character parts and makes them look baby smooth. But that doesn't mean that we actually don't hit the targets anymore, because we'll now reduce the rest of the heights. This might look similar when you're trying to generate a very low lot with a very, very low number of triangles. You might notice that you're starting to lose specific characteristics of your characters. In this case, the eyes start to fall apart. And to address that, you can define important bones, and that basically means that any vertex that is weighted to this bone will be you will be able to bias the amount of reduction that actually is performed on it. So this is what it looks like as a wireframe mode, and in this case we made sure that we don't actually reduce any geometry that's tied to the or skinned by the facial bones, but just as with the free edges feature, we'll now make sure that we'll still hit the vertex or triangle target. So if you're familiar with the montage editor, this might look very familiar. We have our montage sections, you have the ability to preview them, you have your timings for the individual sections, and then your notifies. So this is what it looks like in 4.22, and this is what it might look in 4.23. So everything's now combined into one animation timeline. You can see the actual animation timeline on the bottom has disappeared and is now on the top of this combined widget. And this is very, very similar to how the way that sequencer looks, and it also allows for having this common UX for widgets in our editor. It still, of course, still supports drag and drop, and it comes with a lot of features that will be very similar to you if you've used sequencer before. One thing you might have noticed as well, previewing is now pulled out into a separate tab. So you can still preview your individual sections or all sections, but you can also set up a chain of specific montage sections that you want to preview to see the transitions between them. So that's the montage editor. Next up is the animation editor. Again, very familiar.
So these are the skeletal meshes that make up our constructor class character in Fortnite. These are all things that could be character parts. The body, the head, the beard, the hair. He's got this arm, this like mechanical arm item for gameplay, backpack. This is a little older diagram, but it's still very relevant. Currently, sort of circle, you're going to see that you have the head, the skeleton, the anim blueprint, and the data item. That data item is where we store what scale mesh is it, what anim blueprint is going to be used for it, and material overrides. Does it need a socket? What's the socket name? Anything like that. What's the skin tone? Any of that goes into the data item. That's where the sort of character part data gets stored. You can see we have one for the head, and as we were talking about earlier, it has its own skeleton in anim BP. The body is the same, backpack, the hair, the hat. Oh, gadgets, I didn't even talk about gadgets. So if you play Save the World, you'll notice all of our soldiers have grenades back here, kind of where my mic pack is. So ultimately, we have what we call the CID. That is the character item definition. The HID is the hero item definition, the hero specialization. Now, a lot of these are set up because of Save the World, because if you have played Save, and how many have played Save the World? So, back bling wings. So, we have quite a few tools at our disposal. Anim Dynamics is one. The rigid body node, I should have been more specific just a minute ago when I said physics. I should have on button. There we go. Okay, clothing. So this is Calamity. This is the progressive character I was talking about earlier. So Calamity is she's sort of our frontline example of tech that is currently released to the public. So let's talk about general danglies here. So far, we sort of hit Anim Dynamics, which is, Anim Dynamics is amazing. And we hit Rigid Body Node, which is all. So Rigid Body Node, plain and simple. Here's two things, well, a few options that I want to talk about. Okay, so this is a really cool pickaxe that I did.
The first core aspect of everything we did was built around geometry collection assets. Geometry collections were first introduced as part of the chaos destruction system a number of years ago, and they provide a balance between the capabilities of what we call a static mesh and what we call a skeletal mesh. So if you want many different pieces that can all... Once we have all the assets in the world, we can look at building them into larger structures. So to do this, we had to create the node. So in addition to the connectivity graph, we had to introduce a way for the physics system to actually simulate all these groups as a single unit. On every individual Lego element, we'd start running out of memory extremely quickly. So another major area we wanted to focus on to improve performance was collision. So as probably many of you are aware, collision is generally one of the bigger bottlenecks when it comes to physics performance. So what we want is large, simple shapes, and that allows us to get to the point where we can simulate, tens of thousands of these kind of at any given time. However, it's not quite as simple as saying, let's just kind of throw a box around everything, because that has knock-on effects everywhere. So the example kind of on the top here kind of shows a bit of an extreme case of the type of behavior that we want to support. We have a lot of these like thin railings, large openings that we want characters to be able to navigate through. We also want to be able to build effectively on each of these pieces. So to do this, we effectively created two different representations. We created our physics representation, which is quite simple and works in all of our physics kind of use cases when things are moving throughout the world. And then we created a representation that we use for character movement and for building. That is definitely much more fine-grained, but isn't processed by the physics system. And remember, we're relying everything on our procedural-based data flow kind of nodes. So all these things can be procedurally generated and updated as necessary. So here's an example of one of the ways that we kind of generate our collision. So what we do is we start with our individual Lego elements. We merge them together to form clusters of elements. And then we generate our simplified root collision. In order to prevent these things from, say, covering that door hole, we created something that we called shape protection. So this creates these large spheres that you see kind of in the space. Looks like the video is having a little bit of trouble. But yeah, you can see the large spheres kind of through the door. And then we make sure that any convexes generated do not cross into that space. Now, even with kind of this collision optimization, we wanted to take it further. One of the things that you can start looking at from a physics standpoint is under what situations do you need what granularity of collision? So if you have something, say, rolling across the ground, you want it to behave like the object. So I mentioned moving between tiles as kind of a core problem. So the system that we introduced to try to address this is what we call place-based migration. Another key component is we don't want to necessarily trigger destruction in the same way. So one of the core tenets throughout the system was we should make everything rule-based. We should make it such that everything we put in the world is still going to work as we put more and more constructs in the world. And the reason for that is we wanted to make sure that we could continue to support LEGO Fortnite as a live experience that would continually evolve. So from a destruction standpoint, in order to do that, we created essentially a notion of Another aspect of character interaction that we wanted to be able to support was more two-way coupled-like interactions between characters and physics objects. So ideally, the way we do this is we use something like the physics-based character movement system, which we're releasing as experimental. We also need a new networking model to be able to support the idea of an open-world physics sandbox. So you can see kind of as it's playing in the video on the bottom right, that was effectively what we started with. That was the system that currently, say, Battle Royale uses for kind of networking physics objects. And it's very simple. It just corrects something very forcibly when there's a difference between client and server, and doesn't make any attempt to correct timelines or kind of anything like that to try to prevent the problem in the future. What we introduced was effectively a new correction system that we call predictive interpolation. And we'll go into exactly what that does in a minute, but you can see kind of the difference in behavior that you get once you enable the predictive interpolation system.
Script was brought to our attention. And with the help of our engineers, we were able to recreate all our destructible buildings. This lets us blend up to 4 texture sets on a single asset in a single material element. We focused on a single broadleaf tree. It was more important for us to have lots of variations of the same tree that we can easily compare to each other. We built any variation we could think of, from masked leaves to opaque leaves. Each leaf modeled was a tool, converts it to a skeleton, and then we run a vellum solver on this skeleton to generate the animation. This animation is then transferred back to the tree using UV mapping and the baking of the animation lookup textures. This is a very similar approach to our old pivot painter script. But instead of storing the pivots, we store the animation directly in the texture. This system is effectively manually GPU skinning with a one bone influence. This didn't turn out as we thought. It was actually way slower. And we now had a blueprint that can run geometry script on all of our trees. And we used it as our pipeline tool.
This thing's in the rasterizer, and we were constantly doing the calculation for this effect, even when it was not moving. To combat this, we added a new project-level setting that allows you to enable or disable the evaluation of WPO on a per-object basis. Along with this setting, we added logic to the blueprint and code to only enable WPO for objects while they animate. This helps us detect when we can rasterize these objects using the fixed function fastpath. You can see in this new visualization mode that the object is not evaluating while WPO holds limitations of TSR. And we aim to let them focus on creating new art rather than migrating previously authored art, while not regressing on detailed nanite content.
So, but when he comes in, you want me to just stay right here, though, right? You don't want me to walk down here? I can't walk.
I'd stay right in the middle for when you arrive, before the beat drops. But when the beat drops, then you can just pace around.
No, I'm talking about when he comes in.
Yeah.
Can I still move this way, or should I stay right here?
Stay to that one side. You can still move around, but just stay on that side.
Okay, but I can still move around like up here and stuff?
Yep.
Cool. All right, cool. Let's get it.
All right, Charles, how are we looking? One moment. Could you grab that mic from me? Grab the mic.
So Sean, when you hear it's the first beep, like literally the first beep that you hear, you need to be in for that beat. That's the beat where your feet hit the ground next to him.
Yeah, I know I messed up that one.